Hi and welcome to another edition of Ordinary Differential Equations. Today we are going to talk about the all-important topic of resonance. So let's see what is ahead of us. Resonance is something to hear about in a variety of topics. You see it mentioned in mechanical structures, you could see it in electronic circuits. MRI refers to magnetic resonance imaging, and then you see the topic showing up in other areas, sometimes chemistry, sometimes biology, and so on. Let's go ahead take a look at a simple example of resonance. Well, perhaps not so simple. Maybe we start with the topic of magnetic resonance imaging. So I found this nice little video that tries to explain how MRI works, and some aspects of it are very close to what we are actually doing here. So let's take a look at this demonstration. So let me explain this. Is an 8-minute video. We are not going to be looking at it all here. I'll put the link in the description, and then you can take a look at it. Here the setup, we have a very strong magnet here. You see the South Pole and the North Pole down here, and there is a compass which of course is going to line up with this strong field. Now we want to make this compass to oscillate. So we have access to another magnet here. This is a weak magnet. It can influence this compass some, but not all that much, because there is this strong magnet in this location. So what we are going to do is to move this magnet closer to the compass and then further back, and that's going to cause this compass to oscillate back and forth, somewhat like exactly what happens when two kids are playing on a swing and one of them is pushing the other one. So you have to push the other person at a certain frequency to have that person to swing on a wide angle. Well, something like that applies to MRI as well. If we take a look at this thing, you see that as this magnet moves toward the compass and back, this one oscillates by a few degrees. But if we go ahead and change the frequency at which this moves forward and backward, the issue becomes quite different. So let me fast forward a little bit so that we are not taking too much time. So you notice that oscillations have become much wider now than before. This thing 3 times as big as before. It means we are achieving resonance. The significant issue here is that this weak magnet can compete with the strong one in moving the compass. The way it competes is by repeatedly influencing the compass at a specific frequency and have the energy build up in it so that the amplitude of oscillations become higher. Let's see what's the mathematical version of this. We are going to look at the so-called resonance in pure or undamped oscillations first. Let me remind you what the issue was. When we were writing this differential equation, the first coefficient was mass, the coefficient of y prime was drag force, and the third one was the spring constant. When you don't have that coefficient of y prime, it means you have very little friction or very little drag, and that's referred to as undamped oscillation. So we are going to take a look at this. And there is something special about this that makes it very different from the set of problems we had done before. On the face of it, it looks just the same as the other ones, but it stands out in a special way. Let's see what happens. You remember our method for solving this thing, method of undetermined coefficient, was in two stages. One is to find the solution of the homogeneous, and then write a family of the right hand side, adjust the coefficient until it becomes a solution of this. So let's go ahead. So first step was to go after the homogeneous solution. Homogeneous solution meant remove the external force and just look at this thing with 0 on the right hand side. Solving this thing we had seen a couple of lectures ago. It's quick, so we say r squared plus 4 is equal to 0. That is our characteristic equation. We go ahead and solve this thing. R squared becomes plus or minus 2i. There is no real part here, or if you wish, real part is 0. Excuse me, this is just r, not r squared. So once we have the characteristic roots, we have the solution. The general solution of this thing is going to be a cosine of the frequency is 2t, plus b sine of 2t. If you had, just to remind you, if you had a real part other than 0, that would have come as an exponent of this exponential term, but right now it is 0, exponential of 0 t times this expression, while exponential of 0 t is just 1, and that's why it drops out. So without further ado, let's just remove that. So that's our solution of the homogeneous equation. Then what? Then our next step was to go ahead and find a particular solution. Particular solution would be a solution of that differential equation, and our style of finding it was to go after the family of the right hand side. And the family of right hand side for cosine of 2t, that would have been c, for example, cosine of 2t plus d sine of 2t. Well, when we look at this thing for a second, we realize this is not going to work, and our existing method is going to break down for an obvious reason. This is just like that, and if I take this thing and plug it in my equation, I'm going to get 0, not any multiple of cosine. This is not going to be a good starting point for the particular solution. This falls out. When is it that something like this happens? Exactly when a term of the homogeneous is what is showing up as the forcing term on the right hand side. That's exactly where we have this issue, and we have to essentially up our game and come up with a better strategy. Well, it turns out that across all these cases, the way that we resolve the issue is by multiplying what we wanted to use at the beginning with a factor of t until there is nothing in common between what we have here and what we have on the right hand side. It's possible to make a theory of it, but let's just move ahead and get this ball rolling. So our solution is going to be made out of taking what we wanted to start with, but we multiply with a t until no term here matches the term that we have here. So I'll have c times t cosine of 2t, and then I need to make, in general, I need to make a room for the sine as well, and that one, the whole thing gets multiplied by t, and now I see that this term is not a copy or a multiple of that term, nor is this one, and now we have our solution going to be successful. So what are we supposed to do? We are still applying the method of undetermined coefficient, but our starting trial function is a bit more complicated. So I'm going to go ahead and take a derivative of this thing, plug it back here, set the two sides equal to each other, and figure out what coefficient of c and d will do the job for us. the problem is going to be a little bit more extensive than before, because our differentiation is going to be more time consuming. We have always a factor of t, and therefore we have to apply the product rule, and so on and so forth. So let's go ahead and do it. So y prime p first. Well, as we said, you have to apply the product rule. So I'll have c, derivative of this one is just 1 cosine of 2t, and then derivative of this is minus 2 t, then sine of 2t. Same thing here, derivative first time is just 1, then sine of 2t, derivative of the second term, this is going to be 2 cosine, so I'll have 2 dt cosine of 2t. Okay, we had so fun doing that. We have to do it one more time. It's going to take even more room, so let me start further back here. Y double prime for particular. Derivative of the first one is going to be minus 2 c sine of 2t. Derivative of that, well, it's essentially a copy of exactly what we did there, but if you want to do it all over again, be my guest. And I have made a mistake here again. Let me correct myself. This was a factor of c all over this place and factor of d all over that one. So minus 2 c, derivative of t is 1, then sine of 2t, and then derivative of that is going to be 2 times this, so I'll have minus 4 ct cosine of 2t. So all of this is derivative of this c portion. Notice that this matches that always like that. It always happens that way, just as we had seen before. Now we do the d portion. So I'll have 2d cosine of 2t. Then when I take a derivative of t is 1. Again, we get the exact same term one more time, 2 cosine of 2t. And then I take a derivative of that one. I get minus 4 dt sine of 2t. So let's clean this up so that when we insert in our formula, it's going to be easy on us. This becomes minus 4c sine of 2t, and then minus 4 ct cosine of 2t, and these two add up to 4d cosine of 2t, and this is minus 4d t sine of 2t. Okay, now what now? What's our equation? Our equation is picking one of this and 4 of that, and in this case none of the middle one. Maybe if we do this thing in our head, it's going to be faster than we write it up. So when I take one of this, which means all of that, and add 4 of this to it, what kind of simplifications do I get? That's a standard thing that happens in this kind of problems. Let me see. Do you see it immediately? Let me pause it for a second. So you look at that formula again and tell me what is y double prime plus 4yp. So what do we get? Well, obviously when I add this to 4 of that, and these two cancel each other out, and this very nicely cancel that one out. What's going to be left? So let's write it. 1 y double prime plus 4y. This is all yp's particular solution. So we said the c cancels that c, this d cancels that d. I'm left with minus 4c sine of, sine of 2t, and then I'll have a 4d cosine of 2t. Okay, what do we want from this? We want this to reproduce the right hand side of our original equation, which was 5 cosine of 2t. Well, how is that possible? Obviously there's no sign here, so I need my c to be 0, and 4d has to match 5, so d obviously has to be 5 over 4. Now the general solution, we said as before, is the solution of the homogeneous plus the whole solution of the particular solution we obtained. So here our homogeneous was just a cosine of 2t plus b sine of 2t, and d was coefficient of d sine. So what I get here is okay, so that was the mathematical gymnastic that was involved for getting the general solution of this when there was resonance. So again, let's go back, see what happened. We are solving an equation that on the face of it looks very much like what we had before. What is new here is that the solution of the homogeneous shows up as a forcing term here on the right hand side. One of them, this cosine, here matches that cosine. When you have a commonality between the functions that are in members of homogeneous with what the forcing term that you have here, that's when you have the resonance. Essentially you are shaking a system with its own internal frequency, and that's what's causing all of this problem. Now let's go look at this thing mathematically, see what the issue is. What is why resonance is so significant? So here I have some function a and b. Of course, these problems are determined by the initial conditions. I'm not going to get distracted by that, or just pick some a and b, and then I'm going to compare it with that and see how this presence of this t going to change this solution fundamentally. That is, if you just had these and now you're throwing this into the mix, how is that fundamentally different from that? Before we go to Desmos, can you think about this situation for a second and tell me what do you think the graph of this function going to look like? In what way is it different, fundamentally different from just having any old sine or cosine? Now we have some t times sine of 2t or something. How is the picture going to be different? So think about that for a second, or maybe more than a second. And what do you think? Let's go and check your idea against so suppose I have y of t is equal to, no, a and b, we didn't determine it, but just pick any number you want, it doesn't make a difference. Say cosine of, say I have 2t. Okay, it looks like a nice oscillatory function. If you want to throw another one too, so to cosine sine of 2t, well, still a nice wave, nothing unusual about that. Now if we throw in the last term, the coefficient there was 5 over 4 and such, but that's not a significant component. The significant component was that t, so I write t, and then you see immediately the picture change, sine of 2t. Is this what you were expecting? Let me zoom out here. You see, were you expecting this picture? You see. You see the behavior? What is causing this? You know, there is oscillation becoming bigger and bigger amplitude. What is causing it? Well, it's a factor of t in front. Well, how does that cause it? how come these things are not causing that kind of effect? We didn't see that. Well, this is a constant, 4 or 3 or whatever number it is. That's not changing in time, but this amplitude is changing in time, is growing with time. As this amplitude gets bigger, time passes by, the amplitude is larger and larger, and then your oscillation is just becoming that much stronger. So if you had pure resonance, if you had a circuit that had no friction at all, and you are starting to shake it from outside with its own internal frequency, then the amplitude is going to grow without bound, and in fact it might be something dangerous or peculiar or something, because the energy is just piling up inside of a system. So that is the significance of resonance. Now most physical systems do have a friction in them. There is always some sort of, well, most of them, there is okay, so there's always a y prime, because in most systems there is some drag force or friction, and you can't have that kind of a pure resonance. In some experiments in special circumstances and close to absolute zero, they try to arrange situations without drag force or resistance, but that is of course far beyond where our course is trying to cover. So superconductors and such, you might be able to see something like that there, but in general our typical problem, there is a friction term here, and then you still have this issue. If I have a y prime in this problem, what kind of frequency is going to give me the best response? What kind of frequency is going to give me the highest amplitude of the oscillation? So that's a very interesting topic. If you are interested, you let me know. The project that we have for this course relates to that issue. Okay, now we have covered the most significant type of resonance. In the next lecture we are going to take a look at other cases, more of a mathematical nature, but the situation is rather similar, and then we are going to talk about each of those cases as they come up. Okay, until then, good luck and God bless.